Well, good day, good morning, or good evening, whatever it is. Welcome to the webinar on optimizing the development process with OEMx. All right, good. Checking out all status screens. I'm getting green lights. Let's go. I wanted to let you know we will be sending you a set of the slides, and we will be taking questions at the end. Please don't hesitate to turn in your questions. Just a minute. All right, I saw a little red light. I got it taken care of. Don't hesitate to ask your questions. This is the webinar on optimizing the development process with OEMx. Now we'll be talking about what is this OEMx, and we'll be spending most of our time talking about optimizing the development process because that's the things you're probably most interested in. My name is Bill Goebel. I work for Exida. It was founded in 2000, and I'm proud to say that from a beginning of 2 founders, we have grown to over 200 engineers worldwide in most parts of the world, and we focus on functional safety, alarm management, and cybersecurity. One of our companies does engineering tools. The engineering tools company has 2 suites of tools. One is the Excellentia suite, oriented towards systems level safety design. And the second suite is called OEMx, a suite of tools designed for the development process. Exida also has a certification company, and we're very proud that the certification company has basically grown into the global leader in safety device certifications, according to a study done by Automation Research Corporation Advisory Group in 2014, and we've been growing even more since then. Exida is a very technical company. We're oriented toward research and research to improve development processes, research to improve calculation methods, research to provide better component reliability data, research to improve cybersecurity and alarm management. And we don't keep it all secret, we publish it all. You can see the many books. I don't think there's any organization in the world that has published more material on functional safety, alarm management, and cybersecurity. We have a full set of database books, which we publish in handbooks, and we make available within our tools. Gives you an idea about Exida. Where am I coming from? The development process, the new product development is a tough business. I was a developer and a manager of a development group for over 20 years. And it seemed like no matter what we did, we were behind schedule or over budget. Our management many times called me on the carpet. It's a term we use in the US for, what are you doing? And how come you're not doing better? New product development procedures try to balance the trade-offs, and that's what's so hard. I mean, unless you're making a consumer product where you really don't, there is no safety criticality and you don't care if it fails frequently. And I have purchased several of those products. But in any case, we balance time to market development cost along with safety and reliability for industrial products and vehicles and machines. managers try to create a development process to balance these trade-offs, but a good process can do even more than that. And many engineers have understood the classic chart and the studies that have been done showing that the cost of an error correction increases drastically the further you go. If you catch an error early in the development process, it's much less expensive to correct it. If you catch it much later, especially after production release or deployment, the costs can be extremely high. I've been in both situations in my career. Therefore, I conclude that early design error detection reduces redesign. I mean, that you detect it while you're in context, you fix it, and you don't find it later in system test or worst case after deployment. If you reduce redesign, that reduces development cost and time to market. I concluded after doing a lot of studies on the failures that occurred when I was managing, every time we could detect a problem early in development, I could almost see the time to market shrink. Every time we didn't detect a failure, that's when I went behind schedule and over budget. A common development process, and this is a very, very simplified drawing of a straightforward development process. Now we're not talking about the natural iterations. We're not talking about a wholly iterative process, but the same concepts apply. What we want is to make certain all requirements are met. That's at the top of the list. Number two, we want to find the problems early because that reduces our cost and our schedule. Objective number three, we do need to document the design because that reduces confusion and rework, especially for new people, and allows for a much more effective engineering change process later on, especially after production release. I have so many stories I could tell you about that. It would take the rest of the webinar. But we're going to focus. What we want are faster results, often with less experienced people. At the same time, we'd like a process that helps build our staff skills. And if you're going for functional safety or cybersecurity standards compliance, we want to produce the documents that'll make it easier and faster to get your product certified. Now, here's a far more detailed example of a development process. Now, I don't expect you to absorb all this, but you can look at it when you get your copy of the slides. It's the same fundamental concept with a little more detail, which I will be explaining as we go forward. Let's start with requirements. There are market requirements, maybe regulatory compliance requirements if you're in a regulated industry, risk analysis requirements done by your corporate risk people. That translates and moves into design requirements, which might be classified as safety requirements and non-safety requirements. So what we need to do is get all those documented, classified. Then, in order to make certain we meet objective number one, all requirements have been met, we must specify validation tests. And we need a suite of validation tests that will verify every requirement has been implemented. That's an essential part of most cybersecurity and functional safety standards, and just makes good common sense. There's nothing worse than discovering a requirement that was never implemented during final release testing. Oh, that destroys the cost and the schedule. Once we have good requirements and a suite of validation tests, we can do a safety concept review, especially if we're going to be doing a safety certification. But then we move to system architectures. And I think many of you will find this is the most exciting part of a new design. You draw boxes. You might be drawing on the whiteboard or on the flip chart. And you review them and discuss them, and you say, well, let's try this, or no, and whoop, erase that one and try again, and you come up with designs that you think will work. And then at the high level design, you take and you hierarchically structure the design into more detailed designs, often allocating functions to hardware versus software. Then you create the hardware architecture and the software architecture. And one of the key concepts in a good development process is that we do a quality verification step. And the most common and the proven and valuable verification step for architecture is an FMEA, failure mode and effect analysis. The duty of an FMEA is to find problems early, and we can't really get into the details of learning all about FMEA. We have a couple webinars coming up on that. Stay tuned. But if you find the design problems early, sorry to repeat the message, you can reduce redesign iterations, which reduces cost and schedule. That's big objective. I mean, and the same verification technique works for hardware and software. It's software FMEAs have become the first one have been used for decades. I was first taught the technique in the 1980s. And it's the same concept. You hierarchically design in a structured manner where you go into multiple levels with more and more detail. And typically there's at least 2 levels of detail. Then you do an FMEA on the design. How do we do that? Conventionally speaking, for any functional FMEA, you list all the blocks. You describe the functions required by the block. And for each function, you look at a set of guide words, and they come from the chemical industry. And you use those words to think, to help stimulate brainstorming on what are functional failure modes. No is easy. If it's supposed to store data and it doesn't store data, all right, that's data not stored. Well, more. Too much data was stored. Less. Not enough data was stored. As well as data was stored in 2 places. These are just giving you some idea what these guide words are. And you look at the guide words and you debate and you discuss and you brainstorm to create a list of functional failure modes for each block in the architecture design. But the problem is many people say, well, look, getting from a guide word to a functional failure is not easy. And what if I miss some functional failures? And many of these guide words, I don't understand what they mean in this context. And you got to be careful. It can suck up a lot of time. Then, of course, when you identify something that's bad, then you have to make a recommendation, and you got to, let's call it a mitigation technique. How do you know I don't know. How do you know you've got a good mitigation technique? Well, do the best you can. Then you have to document it all. So you have to take all your information, maybe you were using a spreadsheet, and put it into some kind of a report. The part of the FMEA I liked the least, if you want my own personal opinion. And I have seen over and over again, any experienced FMEA person knows that the results are dependent on the experience and expertise of the FMEA team. You may have a group of people in a meeting for several days on a reasonable design. Once you have an architecture, you can go right into the detailed hardware design, where you take a block and then you actually draw, hardware design engineers draw up the circuitry, specifying the components according to all the rules of the company. When you think you have a circuit that will work well, you might simulate, you might breadboard or prototype the little circuit, or you might go right to PC board, depends on how confident you are, perhaps. But one thing you really should do is do a more detailed analysis called an FMEDA, failure mode effect and diagnostic analysis. And it's really a good idea to do those before you do your hardware prototypes, or at least in parallel with your initial PC board. FMEDA is a quality verification step for hardware design. In many industries, this is done by taking the qualitative FMEA all the way down to the component level. Now, the problem with that is you're still perhaps using guide words, or you have to have a list of known failure modes for any given component. And that's not common. It's not readily available, but it could be done that way. The bottom line is you can read the definition of an FMEDA. Instead of qualitative or even RPN numbers, we actually use failure rate data of the components, generic failure rate data. And if we do it that precisely, there are a lot of benefits, especially for meeting functional safety standards. You can also take advantage of the automatic diagnostic capability that's been planned as part of the architecture and show the value of that quantitatively. And if you have maintenance tests, often called proof tests, you can get the effectiveness right from an FMEDA. How many of the failures will be detected with your proposed manual proof test? And lastly, what's the useful life? All of that can come from an FMEDA. Now, FMEDA is a bottom-up, inductive, quantitative analysis where failure rates and failure modes of each component are used to predict the failure rates and failure modes of the subsystem, and subsystem failure rates and mode are used to subsystem failure rates and failure modes are used to predict the failure rate of the final system, whatever that might be. It's pretty clever, and it generates information we really need for many applications. It's valuable in all applications because you can do a whole lot with that kind of detailed prediction. The software design phase is pretty common. Of course, obviously, you software engineers know that once you have an architecture, a description of the functionality, and you know what functionality is allocated to the software, you can sit down and do your design. And when you have a particular block and a particular function and the data flows in and out, you can sit down and code, create, inspect the detailed software design and the actual source code. Many industrial applications today are done with C or C++. C is an old language, but I think in the certification company, Exida probably sees 90% plus being programmed in C. And then, of course, you have to go through the various levels of testing, starting with unit testing. And we have a a whole book on this kind of thing. But the key point is you can also do a software FMEA, which we talked about. Then you integrate, you put the pieces of software together, maybe in a simulation mode. You put the pieces of hardware together. You may build the whole PC at once or one block at a time. Lately, most people have been building one block at a time, but you still test each block individually. You have to have an integration test plan. I mean, to achieve high quality levels and to really detect the problem. And the integration test plan has to be well thought out. When you have a good thought out, comprehensive integration test plan, you can run the integration testing, you put all pieces together, and finally you have a final device. You really want a good integration test plan established typically during architecture design and the FMEA of the architecture design. When you have a completed device, we can do a black box test, validation test, it's often called, certainly in the 61508 standard. And when you're performing the tests you defined when you were creating the requirements. One test, one or more tests for each requirement. One test could meet multiple requirements. It's a many-to-many relationship. When you're all done, you have a validated product ready for a production release. Now, I am including all the environmental tests and the EMC tests and so forth. But we want more than a good product. We want to reduce time to market. We want to reduce development cost. The primary way to do that is to increase error detection early in the development process. And of course, at exida, we're very focused on the verification steps, the quality verification steps done on the way, which I have talked about. But you got to sit down and think about what takes time. In the failure mode and effect analysis, I've heard a lot of engineers say that they spent a lot of time using the guide words to brainstorm the functional failure modes. Yep, I've experienced that. I've heard them say we spend a lot of time arguing about the value of RPN numbers, which are used in the some companies' versions of the FMEA to establish priority and criticality. But it really sucks up time. Is there a better way? A lot of time is spent discussing possible mitigation measures or recommendations to be put into the FMEA. And it does make sense to create mitigation or recommendations while you're in the context of the design. There's a lot of time spent also keeping track of derived requirements. In other words, I've got a recommendation that represents something that really must be implemented if this product is going to succeed, but it wasn't in the requirements. Well, we got to add it to the requirements. So we call that a derived requirement. Well, I've got to go back to the requirements editor and the requirements tracking tool, or we send it down to the person who does the requirements, and then we have to follow up that they actually entered it, and then we have to make sure a validation test was done. Whoa. It can suck up a lot of time, and I know there are opportunities for improvement in that list. What takes a lot of time in an FMEDA? Well, the number one problem that everybody is talking about is looking up and researching the component failure rate data, especially in all the semiconductors. Understanding where the data comes from, what environment it's valid in, time spent looking at the component failure modes and distributions. There's no failure modes and distributions in any of the conventional standards. And then time spent discussing how good are the automatic diagnostics. It's not good. I know there are opportunities for improvement there as well. And what takes time in all the integration validation testing? Well, a classic old-fashioned approach, which I used to use, we would review keep time for an integration test, and we say, oh, okay, we don't have a plan. I guess we got to stop right now and create the integration test plan. Now I got to go back and review all the requirements again and think, wouldn't it be better if we'd done that while we were in context, when we were really talking about the requirements? Answer, yes. Time spent linking test objectives back to requirements. How do we know the validation tests cover all requirements? You must link them back and forth, forward, backward traceability. Time spent reviewing architecture designs to create the integration test objectives. Oh my. I wish I'd done that back when we were doing the FMEA. But most people don't. Most FMEA procedures do not even mention thinking about and defining integration test objectives right then and there. And if you have good linking between implementations and integration tests, when you make a design change, especially when you discover a problem during prototype testing, if you have a good link between implementation and integration tests, you can pretty much hit a button and it'll tell you what tests you have to repeat when a design change is made. If you don't have that, you've got to spend some time looking at all the tests and thinking about them. And maybe you'll get them and maybe you won't. And finally, my favorite topic, time writing test reports. There's opportunity for improvement. So right now, think about what we want is to optimize the time spent on the verification steps, while not only increasing the error detection probability, but decreasing the man hours. So the goals are to increase our accuracy, improve the design. I'll say not design rigor, but I'll say design quality. Reduce the engineering time, which reduces cost, improves design quality, exposes them earlier, all the things we've been looking for. And if you do it properly and you're getting functional safety or cybersecurity certification, and it'd really be good if we had a single tool for hardware, software, functional safety, or cybersecurity. So we don't have to flip back and forth with different tools with different vocabularies and different commands. OEMx is a suite of tools designed to be part of the engineering process. At the moment, there's 3 applications, RecX, ArcX, and FMEDAX. These tools are meant to play nicely together. They provide a good seamless integration and data sharing. There's a common set of support functions for defining tests, defining action items, and so forth, and linking traceability between requirements, validation tests, and implementation. There is tool qualification reports available for functional safety in general industry or automotive or machine. These common features are requirements and implementation and test tracking, action items, report generation, and derived requirements. If you're in the middle of an FMEA, you make a recommendation, and you can hit a button that'll be entered right into your requirements document. This is important because we want to be able to typically trace between market business requirements, functional requirements, and safety requirements, And we want to show the validation test objectives for each requirements. And of course, if it's safety requirements, we have a checklist for our user manual to make sure everything that's supposed to be in the safety manual is there. The most important linking and tracking we've talked about, the tracking between safety requirements and the validation test. It's always good to make certain all your requirements are met, but it's essential if you're building products for safety critical applications and especially for functional safety certification. The OEMx tool has a test objective editor, which allows you to specify validation tests and log them into the test report, which then can be used to do the detailed test plan, which is pretty nice. Next, ArcX. It's an advanced FMEA tool that shows a structured hierarchical design in a tree format. And the advantage of that is that it's a well-known technique and generally and quite quick to understand. Now, the second one is a pretty big deal. It provides a knowledge base of known functional failure modes and known well-proven mitigation techniques. One person who saw a demo of ArcX said, "Oh my goodness, it's an instant FMEA." Well, it's not quite an instant FMEA. You've got to press some buttons, but I'll tell you, it's a whole lot faster than conventional techniques that are in common usage today. And ArcX provides a common method for hardware, software, and cybersecurity. This knowledge base is based on a lot of years of experience. People at Exida have been doing FMEAs for decades on both hardware and software. It's clear that design patterns have emerged. There are common failure modes for functional block types in both hardware and software and FPGA implementations. And so we have common failure modes for block types that have been documented over many years of experience. And the mitigation techniques are well known. They're not specific for any specific design. And of course, there are many proven mitigation techniques. Wouldn't it be great to just see a list of them? And that's exactly what we do, and we call that the knowledge base. Common failure modes, functional failure modes for block types, and proven mitigation techniques for most of those failure modes. What's nice about it is it's a context-specific list of failure modes for hardware, for software, for FPGAs, and cybersecurity issues. It's a common list of mitigation techniques for hardware, software, FPGAs, or cybersecurity. And it's based on a lot of experience. And the neat thing about it is you may have a lot of your own knowledge, known mitigation techniques. You've invented something that nobody else has. You can type that right in and it'll go into your corporate knowledge base, which is maintained in the ArcX tool. The objective, make the FMEA process much quicker and more effective. And it's primarily done with an instant knowledge base. We reduce the chance of an error of omission, and it takes a lot less time. Derived requirements are absolutely easy to implement when you're doing the FMEA, you just hit the test button. The test editor will come up and it will allow you to enter new requirements and new validation tests. The tracking tool will allow you to specify specific integration tests that become very clear when you're in the context of the architecture design. It's just, I can't speak for everyone, but I know when I go out of context, I wait a few weeks or even a few months and I come back and says, what was that for? Don't worry, do the job when you're in context. The FMEDAX tool is an integrated FMEA tool. I think the most important part about it is the component database, which saves a lot of time on research. The embedded component data takes advantage of all the knowledge that has been gained at exida over decades. On average, if you go to do component data research yourself, studies from our customers have shown that it takes an average of 40 hours per part. Just think of how much time you can save with a component reliability database. The FMEDA can be done on each subsystem. And one advantage of that is you can duplicate. Often there are 2 or 3 instances of some, maybe even 16 instances of some subsystems, like digital input channel. Many modules will have many digital inputs or analog inputs or outputs. You typically don't have too many instances of the main central microcomputing, but once you've done a subsystem, if you use the same subsystem in a new design, you can copy the whole subsystem design right into your new product, FMEDA. Some products are used in different environmental profiles, and the FMEDAX tool allows you to quickly change from one set of environmental profiles to another, and the failure rates will update. You have to go in and change almost every single failure rate when this happens. I just don't understand. I've done it in a spreadsheet. It was unbelievably painful. And by that, I mean time consuming and error prone. All the calculations are done for you, as they probably would be in a well-written spreadsheet, but it's important that you have all the information you need to not only calculate end results, but figure out where the trouble comes from. If your failure rates are higher than they must be for your performance level. The OEMx tools use a combination method where the output of a FMEA and the failure modes for the blocks are fed directly into the FMEDA. And that's extremely helpful because you don't have to re-enter any of that. Whereas a conventional approach is to use a common FMEA tool and then type these failure modes over again in a spreadsheet. It's nice not to have to do that. And in the end, it's not only time consuming, but it's potentially error prone. Save time, increase design quality. The FMEDAX tool has a component editor. You enter the component type. The failure modes and the failure rates are displayed when you hit the assign CRD button. The failure modes are already entered into the tree. You pick the failure mode that you map. And when you're all done, you can calculate the results. It's pretty fast. It's neat. Now, FMEDA outputs should be failure rates per failure mode or for each functional safety category. It should also generate the useful life of a device or a system based on the useful life of the components. Usually worst case wins. It will tell you the diagnostic coverage factors for each failure mode and the coverage factors for each defined manual maintenance test. We call it a proof test. When you're all done, you just take a look at the results, and there are some error checking features. Over allocated and under allocated, they both should be 0. If you forget to map, you get an under allocated warning. If you've mapped more than once for the same component, you get an over allocated warning. And then you get the end results for both the IEC functional safety standard and the ISO 262 functional safety standard. Action items can be created any time. There's a suite of reports that can be generated. They can be generated when you haven't even done the work yet, but that's a waste because they're kind of empty. But you can generate an FMEA report, a summary report, a consistency check report, safety manual contact report, all the things that are really good to speed up product development and product development activities. They're all generated in Word and can be edited and copy pasted as required. We're doing good right on time. Just remember the OEMx tools are created for requirements, for architecture of FMEA and for FMEDA. We want to achieve the objectives of a good development process. I hope you can understand how by optimizing the verification, we can improve design quality by finding problems early, which also then reduces time to market and development costs. Now, FMEAs and FMEDAs can absolutely be done with spreadsheets or with a commercial tool. However, no matter what you do, please think about using next generation methods. And many commercial and some commercial tools have these new methods embedded. Now, I'd like to take any questions anybody has. Let me look at I'm looking at my questions monitor. I don't see anything on the type yet, but think about what you've been seeing. We'd very much like to hear if you have any questions or comments. I'll stay on as long as we need to show that. Question. In the last session, I had an important and useful question on where does the component reliability data come from for your FMEDAX tool? There was a reference to the CRD, the Component Reliability Database, and that is a database that is researched and compiled by a group of exida engineers. And basically, there's a cumulative total of about 2 full-time people working on this every year. You ask why? Siemens SN 29500 hasn't been updated in years. Yeah, I know, but think of all the new technology that has come about in the last 5 years. And it's not just the semiconductor people, they are doing amazing things. But even capacitors, the chemistry has been improved. The construction of some capacitors has improved. power transistors, the material, the gallium arsenide or the gallium nitrate, instead of pure silicon, handles a lot more power with a lot, and it has with a lot more efficiency. Motor controllers and motors are now getting more efficient every year, which is good. I'd like to get more miles per charge on an electric car. There's a lot of work being done for that right now, as you might imagine. All right, I see something here. Let me, what else? Oh, in the architecture, two functions can share one component. Yes, that's true. For an example, a MUX A to D can be used to monitor a temperature and a voltage. Here are two architectural functions mapped to one component. Generally speaking, I have been able to draw my architecture drawings so that there is a fixed set of components per block. And I would simply recommend that you isolate the common component as a separate block in the FMEA block diagram. Good question, though. Thank you very much. There are other solutions. If you want, you can only enter the component in the first block, so you don't double count. But I think that's more confusing than just making it a separate block. There's actually a lot of tips and techniques on how to do better FMEAs faster. And we've got some webinars coming up on that. Same thing with FMEDA. The next webinar series coming up is the FMEDA series. And there's a total of, I don't know, I think it's 6 webinars going through the entire FMEDA process. Stay tuned. There's a lot of good stuff coming. And as you know, these are free. We also have paid training courses, and Exida does a lot of this work as a service. All right. I don't see any other questions right now. If you have another question, do not hesitate to send in an email to us, and we can give you a good answer asynchronously. All right. Thank you all very much for your time. I hope this has been useful. Please don't hesitate to let us know your comments, good and bad, and your questions. Take care. Bye-bye.